Good morning, children. Sairam. Children, I hope you all are safe at your places. Children, in the previous presentation, we have started with the chapter Classification of Elements and Periodicity in Properties, the third chapter of your NCERT book. Now, children, I have told you there are three topics to be covered. The first one, that is modern periodic law and the present form of periodic table, we have already done in the previous presentation. The nomenclature of elements with atomic number greater than 100 also is already done. So today we are starting with the third topic of the chapter, that is the periodic trend in properties of elements. In that we have to discuss the atomic radii, ionic radii, inert gas radii, ionization enthalpy, electron gain enthalpy, electronegativity and valency. Children, I know you already know about what is ionization enthalpy, what is electron gain enthalpy, what is valency. You all have already learned about this in standard 10th. But here we will study how the variation of these enthalpies takes place when we move from left to right in the periodic table, when we move from this side to this side, or from top to bottom in the periodic table. So today we'll start first with the atomic or ionic radii. Now, before learning how the variation take place, you should be knowing what is the meaning of the word atomic radii. Now, see, if suppose we are talking about the non-metallic elements, if we want to know what is the atomic radii for non-metals, then how we will calculate? We have to measure the distance between the two atoms when they are bonded together by single covalent bond, or for forming bonding a covalent molecule, it is called the atomic radii. Half of that is called the atomic radii. Like for example, this is one chlorine atom, that is a non-metal. It is bonded to another chlorine atom and forming the Cl molecule. In these two, will take the distance between the two nucleus and take half of it as the atomic radii of chlorine atom. Children, for example, you all can see here it is given that the internuclear distance between the two atoms is 198 picometer. So, half of it, 99 picometer, will be taken as the atomic radii of chlorine. This was the case of non-metals. If suppose we are talking about the metals, for metals, the half of the internuclear distance separating the metal cores in the metallic crystal. If we are talking about the metals, we'll take the example of metallic crystal and we'll see the distance between half of the distance between the two metal cores. That means metal cores, the distance between the metal cores divided by 2 will give you the metallic radii. For example, the distance between two solid copper atoms is 256 picometer. So, the metallic radius of copper will be 128 picometer. Children, I hope you have understood what is atomic radii in case of metals and in case of non-metals. Now, coming to the important point, that is the variation of atomic radii in the group or in a period, how the variation takes place. So, we can say that atomic radii refers to both covalent or metallic radii depending upon the element is a metal or a non-metal. Now, there are various techniques by which we can measure the atomic radii, that is either the covalent radii or the metallic radii, like X-ray or other spectroscopical techniques. Now see how the variation takes place along a period. Now see lithium, beryllium, then the D block elements are there. After that, boron, carbon, nitrogen, oxygen and fluorine. That means we are moving from left to right in the periodic table, that is variation atomic radii with atomic number across the second period. Here you can say on this axis we have taken the atomic radii, that is increasing upwards, and here the atomic number is increasing from 2 to 10. Now see, for lithium the atomic radii is quite high, that is around 158 or 57 you can say. For beryllium it is around 110. For boron it is around 90. For carbon it is less than 80. For nitrogen also less than 80. For oxygen around 50. And for fluorine also you can say it is around 50. That means the atomic radii is decreasing when we are moving from beryllium towards oxygen. Now why this thing happens? Why the atomic radii decreases along a period? It is because the electrons are added in the same shell. No new shell is added, and the electron is added in the same shell. The effective nuclear charge increases, because along with the addition of an electron the protons are also added, so effective nuclear charge increases and the atomic radii decreases. Now if suppose we are talking for variation along a period, how the variation takes place along a period? See, this is lithium, sodium, potassium, rubidium, cesium. It's not a period, sorry, it's a group. That means lithium, sodium, potassium, rubidium and cesium. We are moving from top to bottom in a group. Now see how in a group atomic radii varies. For lithium it is around 150 picometer. For sodium it is more than that. For potassium it is more. For rubidium also it is quite higher compared to potassium, and for cesium also it is 262. That means the value of atomic radii from lithium to cesium along a group is increasing. From fluorine, chlorine, bromine, iodine also it is increasing. Why the increase takes place along a group? It is because new shells are added. Like for example, lithium was having 2 shells, sodium is having 3 shells. So we can say the atomic radii is increasing. So now it must be clear to you that along a period the atomic radii decreases, or you can simply say size of atom decreases, and along a group the size of atom increases. You can simply learn it by, this is period. Along a period, when you are moving from left to right, the atomic radii is decreasing, and along a group it is increasing. The atomic radii is increasing, the size of atom is also increasing. Now coming to the second important trend, that is ionization enthalpy. I hope you already know what is ionization enthalpy. It is the energy required to remove the outermost electron from an isolated gaseous atom in its ground state. It is always positive. Endothermic means positive. The sign of delta H will be positive. Enthalpy change will be positive. That is, for an ionization enthalpy we write IE. The ionization enthalpy is equal to positive value. Now this positive value, how it varies along a group or a period. See. Now see, here we have taken the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. That means we are moving from left to right in a period. Now in the left to right in a period, you all can see for lithium the value is 520. It is in kilojoules per mole. For beryllium, it is higher, very high. It is 899. For boron, it is quite less. It is decreasing. And further, it is increasing, then decreasing, and then increasing. In general, you can say from left to right, the ionization enthalpy increases with a few exceptions, like boron is having lesser than beryllium, oxygen is having lesser than fluorine. Why is it so? It is because for beryllium, if you see, the atomic number is 4. Configuration will be 1s2, 2s2. Now, in the second shell, only S subshell is there and it is completely filled, and taking out electron requires a lot of energy. So, for beryllium, it is quite high. After that, it again follows the normal trend up to nitrogen, but for oxygen it is less. Why for nitrogen it is very high? Again, the same reason is there, and the reason is for nitrogen the atomic number is 7 and the configuration is 1s2, 2s2, 2p3. That means p subshell, 3 electrons are there, 1, 2 and 3. This presence of 3 electrons in the p subshell makes it half filled, and half filled configuration is extra stable. Why it is stable? Because it is having uniform distribution in the in all the orbitals, but singly filled, so it is extra stable. After that also it again follows the same trend. So you can simply say from left to right in a period, the value of ionization enthalpy increases because the size of atom decreases, as we have learned in the previous part that the size of atom is decreasing. Now coming to the variation along a group, lithium, sodium, potassium, rubidium and cesium. From here to here, you all can see it is continuously decreasing. Why there is a decrease? Because the size of atom is increasing, so ionization enthalpy decreases. Now, so we have done 2 of the trends. The first was atomic radii and the second is ionization enthalpy. Now, how they are varying, let us see in the periodic table. First, talking about the size or the atomic radii. From left to right, the atomic radii decreases. From top to bottom, the atomic radii increases. Now coming to ionization enthalpy. For ionization enthalpy, from left to right, the ionization enthalpy increases, and top to bottom ionization enthalpy decreases. Here it is increasing because the size is decreasing. Here it is decreasing because the size is increasing. So we have done 2 of the properties. Now coming to the third property. Before the third property, you all can see this trend in the variation of first ionization enthalpy from atomic numbers 1 to 60. The same trend is followed here, that along a group it is decreasing, along a period it is increasing. Now, the third important trend that we have to study is the electron gain enthalpy. What is electron gain enthalpy? When an electron is added to the neutral gaseous atom to convert it into an ion, when the electron is taken by the atom, it accompanies the energy change that is called the electron gain enthalpy. Now, one thing you have to remember is electron gain enthalpy can be positive or negative. It can be an endothermic process. It will be an endothermic process in case of metals, because they don't want to take electron. We have to add the electron forcefully. And it will be an exothermic process in case of non-metals, because they actually want electron. When they get electron, they give out energy and become stable. Now, for example, 17th group element are having very high negative electron gain enthalpy, whereas the noble gases have large positive energy. Why? Because the noble gas, they don't want to take the electron, they don't want any electron, they will not take any electron. Forcefully we have to make an electron to be added in the last shell, so it is highly positive. Whereas fluorine, it wants electrons, so it is negative. Now how the electron gain enthalpy changes when we are moving along a group or a period? See, you can simply say that for metals, the electron gain enthalpy, coming to the periodic table, see, for metals, the electron gain enthalpy is positive. We have to apply energy. For sodium, for these metals, it is highly positive. That means a lot of energy is required. So, down the group, the value of this positive value, it decreases. From top to bottom, the positive value decreases because the size of atom is increasing. From here to here, you can say the positive sign changes to negative sign and becomes more negative. From left to right, it becomes more negative. And for these non-metals, if we are moving from top to bottom, it is negative, but it becomes lesser negative towards the bottom. Clear? Now, coming to the fourth important property, that is electronegativity. It is a qualitative measure of ability of an atom in a chemical compound to attract the shared pair of electron towards itself. See, till now you all were learning that electronegativity is the tendency to take electron and attain a negative charge. But you will not say like this now. You will better say it is the tendency to attract the shared pair of electron towards itself. We cannot measure this quantity. It is not a measurable quantity. In general, we say that it increases across a period because non-metals are more electronegative from left to right, and decreases down the group because here the metallic character is increasing. See, in this periodic table, this side, these are the metals and these are the non-metals. From here to here, the electronegativity increases, and from top to bottom, whether it is here or it is here, it decreases because the metallic character is increasing. See, next, the fifth property is periodicity in valency. The valency of element is usually that it is equal to the number of electrons in the outermost orbital, or 8 minus the number of electrons in the outermost orbital. Now you all can see how the valency changes from left to right. For the first element, the number of valence electrons is 1, then 2, then 3, then 4, then 5, then 6, then 7, and then 8. Valency will be again 2, 3, 4. From here it can be either 3 or 5, 2 or 6, 1 or 7, or it is very less. For the 18th group element, it is almost 0. Now see, you all have already learnt about valency, so we will not go in detail. Now next is the periodic trends in chemical properties. Here just with the help of arrows, it is shown to you how the properties are changing. The first was atomic and ionic radii. I have told you the atomic radii from top to bottom is increasing. From here to here it is decreasing. The second property that we have learned was ionization enthalpy. Ionization enthalpy along a period increases, along a group it decreases. The third that we have learned is electron gain enthalpy. Electron gain enthalpy from left to right becomes more negative, and top to bottom it becomes positive. Next is ionization enthalpy. I have already discussed electronegativity. Electronegativity from top to bottom decreases, and from left to right it increases. So these trends you have to remember, and this was the last topic of the chapter. In the previous presentation only I have told you, you have to do the questions of this chapter in your fair notebook. Copy down the PDF for the NCERT solution and write down the questions and answers in your notebook. There is no numerical in the chapter. It is a chapter of, you can say, inorganics. So theory questions are there. You can do it yourself. I will request you to download the PDF and write down the answers in your notebook. Thank you. Sai Ram.